This is Radio Ecoshock with Alex Smith.
Beyond humans, the sea hosts a dance of chemicals and living things that affect climate change. We get a view of that hidden ocean through the work of Christoph Heinze. At the University of Bergen and the Bergen Center for Climate Research, Professor Heinze is Professor of Chemical Oceanography. In this interview, we focus on just one of his many specialties, feedbacks between biogeochemistry and climate. From Bergen, Norway, Christoph Heinze, welcome to Radio Ecoshock.
Yeah, thank you. Good morning.
In a paper just published by PNAS, March 2021, you discuss, quote, the quiet crossing of ocean tipping points. Why don't we start with a kind of switch in the ocean which reduces the amount of oxygen vital for life? How could oxygen become depleted as climate change develops?
Yeah, so one of the main reasons why we expect that oxygen will go down significantly in the ocean is due to the warming. And oxygen is a gas, and it gets dissolved in seawater. And the warmer the seawater is, the less oxygen gets dissolved. And due to this temperature-dependent solubility, there will be less oxygen expected in the future in the ocean. The other problem is that also the ocean circulation will change, and this relates to the oxygen as well. If we have a slower overturning circulation, the mixing of waters from the surface into the deep gets slower. More organic particulate matter can reach the deep sea and it gets remineralized there, drawing down the oxygen as well. And in some areas also we will get regionally probably an increase in upwelling, and this promotes more biological production. And due to this process, there will be more organic material sinking through the water column and using up the oxygen as well. A further problem is then other factors, such as, for example, the transport of reactive nitrogen into the ocean through rivers and also through the atmosphere, which will promote further biological production and make the oxygen problem even bigger.
Well, people call them dead zones, but does it really matter if these pop up in regional areas? I mean, does that affect the big global picture?
I mean, it's one has to see that all these fragmented changes add up to a big problem altogether, and there are of course some more regional or local deoxygenation events, but for example in the Pacific, in the Western and Northern Pacific, it's a problem which extends over a wide area of the ocean.
Well, yes, you raised the problem of gradual changes which add up to extreme impacts over time. Humans tend to focus on a chain of catastrophes while ignoring creeping changes. It's like a flaw in our perception almost. Why do we need to watch for gradual change in our environment?
Yeah, so specifically for the ocean, it's so that, for example, the ocean is a big heat sink and CO2 sink. So let's say man-made sink for man-made CO2 and man-made heating, and it does a big service to society by this. But we have to pay a price because the heat and the carbon that has been taken up by the ocean gets mixed into the interior of the ocean and thus providing a heat and CO2 sink, but on the other hand, changing the oceanic environment and mixing heat and CO2 into areas which have a long overturning time. So the overturning time scale for the ocean circulation is around 1,200, 1,500 years. So if we mix in the CO2 and the heat into the ocean, and even if we would cool the atmosphere, even if we would take out a lot of CO2 out of the atmosphere, it would take a very long time to get the CO2 and the heat back from the deep ocean into the atmosphere or into some other reservoirs. So that's in some way we are trapped by the oceanic timescales here, and this makes the changes on human timescales crazy. Or many of the changes that are ongoing, many of the creeping changes which are ongoing, quasi irreversible on human timescales.
And what do the best Earth system models predict in those subpolar North Atlantic waters if we continue towards a high CO2 future?
Yeah, so that one of the thing is that these areas are critical for the overturning circulation and the production of deep water. That will probably get less deep water production. So we expect the most of the Earth system models describe, for example, that the Atlantic meridional overturning circulation will slow down. So this is the Earth system models are in fairly good agreement concerning this, at least on the qualitative side. On the other side, always when we have deep water production, there will be a strong downward transport of carbon or CO2, which dissolves or dissociates in ocean water to mostly bicarbonate. And the oceanic carbon system is such that if you add CO2, you decrease the pH, so you acidify the water. And by this deep water production, also carbon is mixed down to greater depths. So per square meter, the North Atlantic is the strongest CO2 sink in the world ocean. If you don't look at specifically per unit area, then of course the tropics are very important in the Southern Ocean. But if you look per square meter, then the North Atlantic is a very strong sink of CO2, with the implications that you mix down low pH water also quite fast into great depth.
Yes, in another paper you suggested that we should be monitoring the pH at great depth and in a couple of different locations of the world. How good a job are we doing at? Do we really know how much acidification is happening in the world's oceans?
Yeah, so the acidification can be very well monitored and very well predicted. It's one of the variables that we have a fairly good handle on. Of course, we have many more measurements of the CO2 partial pressure and also the pH at the sea surface than in deep waters, but also the time scales of the deep waters are a little bit slower. So that repeat hydrography every few years already helps in diagnosing this. And there are also floats being developed that can, hopefully in foreseeable future, measure this also 3D. But we have quite a good handle on that. And we would like to have more time series stations at one position so that we could monitor this more reliably and at fixed positions, and have a larger data set to calibrate the models. But it's already quite good. And the spread in the pH, as predicted by the models, is not so big. So I think that this is working quite well. Of course, every of these Earth system models, they have differences in their ocean circulation and hence differences in the details of the distributions. But overall, I think that ocean acidification can be documented and projected fairly well.
Are there tipping points lurking in ocean acidification or its impacts on living things?
Have I understood you want to know whether living organisms, whether there are tipping points for living organisms?
In ocean acidification, do we come to a certain point and then it will be much clearer to the public the impacts of this?
Yeah. So the ocean acidification impact is a complex one. And there are especially calcium carbonate shell or organisms that produce shells out of calcium carbonate material, calcite and aragonite, and other mineral calcium carbonate minerals. They suffer most. There are a few organisms also who benefit from it. But one of the key examples for a joint impact of warming and pH change are the corals, the warm water corals. There we can see that they suffer and change, and it's when it comes to details, it's sometimes difficult to decide which process is decisive for the local change of corals. In some cases it's the temperature which is dominating. In others, also the pH change plays a role. But there it's quite clear that it's one of the well-established cases where we see a big impact on ecosystems. And this impact, or this hazard first, and the following up impact, they cannot be remedied easily. We lose their organisms which have been built up over millions and millions of years, and they cannot be recreated, even if the conditions theoretically would change back to the pre-industrial.
In 2017, you co-authored a paper about an amplification of global warming by a process seldom discussed outside specialty science. What is marine dimethyl sulfide, and how could it make human-induced warming worse?
Yeah, so dimethyl sulfide is a substance which is produced by organisms, by phytoplankton in the sea surface, specifically by organisms that produce also calcareous shells. So if we reduce the phytoplankton that produces this DMS, then there is also less production of DMS. And what is this DMS is one of the key sources in the Earth system to produce sulfur aerosols, which also serve as condensation nuclei for clouds, and therefore there is quite a change in the Earth system due to this process, where some details, of course, are not understood, but it's one of the examples where you can see that the anthropogenic forcing, ocean physics, biogeochemistry, in the end also feedback back to the atmosphere, and mediated through organisms. And if one includes that process with the pH-dependent DMS, then one would get a somewhat stronger warming in the end.
Well, this is wild because we're talking about sulfates coming from natural sources that could change the albedo of the Earth. But, you know, we have suggestions for geoengineering where we will blast up sulfates to reflect more of the sun's energy away to help cool the Earth. But at the same time, climate change may be reducing the natural source of those sulfates that were cooling us already.
Mm-hmm. Yeah. So it's a complicated system, and there can also be some surprises in it when it comes to this technical mitigation or geoengineering with artificial sulfur aerosols changing the albedo of the Earth. One has to see that it's also maybe problematic because one would maybe have a little effect or some effect on the temperature, but we don't know what happens if we do this, and if, for example, ocean currents would change due to this mitigation option. Then we don't know if an ocean current has changed, whether if you and it changes in a way we wouldn't have expected, and we would like to stop that. Then we may stop the artificial sulfur supply to the atmosphere, and the albedo effect would go away, but the ocean current would stay as potentially as it was in this unwanted way. So I'm a bit skeptical about geoengineering, whether it really would help. It's important to look at it and to understand it, but I am very skeptical whether we would possibly create more problems that we would solve through it. But this is a bit of personal, so I'm speaking more as a citizen in the moment. But I think one has to be very careful with it, and I think many people think in the same way. But therefore, it's of course good to do research on it, to find out about it, and to participate in a qualified discussion.
Well, meanwhile, we could try and keep our natural sources alive.
You're listening to Ecoshock Radio for the world.
I'm Alex Smith. Get it all at our website, ecoshock.org. This is Radio Ecoshock. I'm Alex Smith. My guest is Christoph Heinze from Bergen, Norway, and we're talking about a wide range of his scientific work. Now, Christoph, most of my expert interviews on the ocean concentrate on the growing impacts of heat in the sea, and it could be warm waters going under the ice sheets, killing coral or powering up hurricanes. But you just raised three other ocean feedbacks: oxygen depletion, acidification, natural sulfur emissions. Why do you say these tipping points may arrive before we really see the worst of the heat impact?
Yes, yeah. So it's for example, for the deoxygenation, we see it going on, though not very clearly. For the ocean acidification, it's very well documented, much better than for oxygen. For the heat, it's well documented. We have increasing numbers of heat waves. We have seen examples where heat waves work like a shock that can induce a regime shift in ecosystems, and all these changes are documented and are in part happening, and are of high probability. So that we will acidify the ocean further is completely clear. Even if we would switch off immediately the emission, there would still be some legacy happening, and the ocean would acidify further. So there's no discussion about it whether it happens. It's only the question whether to which extent it will happen in the next decades and centuries, and this depends on our behavior as human beings. So these are high probability tipping points which happen at the regional and probably potentially basin-wide scale, which add up to a big global problem. But this. These high probability tipping points will also have a significant impact. I would like to stress at the same time that I think that one should take the singular big events due to tipping points, such as the instability of the Western Arctic ice sheet, for example, or a potential shutdown of the meridional overturning circulation, equally seriously, because they are not so likely, maybe, don't have such a high probability, but they will have a tremendous impact, and therefore, though they are not so likely, if they would happen, that would be very bad. Therefore, I don't advertise for a competition between the tipping points here, not at all. All of them are very important, and one has to look at them. Has to look at all of them very critically and try the best to avoid that we cross the respective thresholds, or let's say the planetary boundaries, which are being established and have been established, and they need a refinement and the quantification to make humankind staying in the safe operating space, even if already a lot of changes have happened. But this is one of the goals, that we limit the damage being done to the Earth system. So that's one of our key tasks, I think, also as scientists, to contribute to that damage limitation.
The big climate models, including those employed by the Intergovernmental Panel on Climate Change, do they include these possible climate accelerators in the ocean that you've been talking about?
Yeah, they do, and especially they all do, especially the special IPCC report on the ocean and cryosphere has a very good and also detailed discussion on extremes and tipping points and reversibility and the associated hazards. And there is also, in one of the chapters of this report, there's a very nice table on abrupt changes in the cryosphere and in the ocean, and also discussing the probability and the impact and the reversibility of these tipping points. And it's a very good resource. It's a very well written report with a wealth of information. I really recommend experts and non-experts to study it with excellent figures. And
is it too early to put numbers to these other ocean processes that could accelerate global heat? How significant are they?
Yeah, so this is a complex matter which needs following up with respect to many details, and but overall the big picture is quite well known, that the addition of heat to the ocean will change the density stratification, will slow down the meridional overturning circulation. We don't know whether it would lead to a really severe shutdown or not. This is being under discussed. It's controversially discussed, and it's then not the final word is spoken. It's currently not deemed to happen, let's say, in the next few decades. That is not so likely. But there can be surprises in the system. But overall, we have a quite good picture when it comes to the carbon, which has been taken up by the ocean. We know that it will stay there for a very long time. Even if we would, let's say, if a part of the ocean can take up about 11/12 of a perturbation to the atmosphere. So there will be, when this happens, the CO2 will be in the ocean. There will be a new equilibrium. The atmosphere will be at a CO2 level which is higher than the pre-industrial, basically forever, and the ocean stores a lot more carbon than before the industrialization. And if there are no other processes, either human beings taking out the CO2 from the atmosphere through artificial trees or any other capturing mechanism, or if the land biosphere would not possibly take out some carbon over time through new peat production over a very long time, then we would change the atmospheric CO2 content and also the oceanic CO2 content for to some degree forever. Yeah, and of course there can be other mechanisms such as volcanism and so on also going on, but it's a little bit frightening that the imprint the humans do to the globe within a few decades and centuries will have an imprint over a very long time, just by the mechanisms which are built into the system. And so this has to be taken into account as well in the long time perspective. And I think you had also David Archer here reporting about this.
Yes, we had David Archer on a couple of weeks ago. So, Christoph Heinze, you are a German now deeply embedded in research in Norway. How did that develop?
Yeah, so that was quite interesting. I worked for a long time in Hamburg and at the Max Planck Institute of Meteorology and also the university, and then I got then an offer later on to go to Denmark to work more in an institute more oriented to ecology, and then I had an EU project running, and I was asked also by some people also from the community and the European Commission whether there would be a big sources and sinks assessment plan by the ocean. And I said, yeah, probably we could do it. And I got a very big project, a very big grant, or it was in preparation. And at the Bergen Center, they were looking for somebody with my expertise and offered good environment to host the project. And then I made my way from Hamburg and also Scandinavia a little bit further north to Bergen. And since then I'm running a series, or I ran a series of projects, and now is also one ongoing. It's called this Comfort project. It's funded by the EU, and on tipping points in the ocean. And this is how my career went. And maybe I'm going northward more and more. I don't know where I will end up in the end.
Yes, I've been in northern Canada, but I find myself in my senior years in southern Canada, where it's just a little bit more comfortable. So, as we wrap up here, are there still mysteries in ocean science that you would like to tackle or see moved up as priorities for the international community?
Oh yeah, I mean, one of the things which is puzzling me is, I say two things. One is, so we expect that the meridional overturning circulation will get weaker. That would imply that also the biological production rate, the primary production, the phytoplankton production would go down. Will this lead to any significant changes in living biomass or not? This is one of the questions which I find intriguing, and where I don't know whether there is an answer out. The other thing is that this weakening of the overturning circulation happened also in the last glacial maximum about 20,000 years ago, when it was much colder on the globe. And this is, I find, one of the puzzling things. Probably the weaker circulation during the glacial was different than the weaker circulation we will get in a few decades. But nevertheless, are we at some kind of maximum circulation in the moment, or how is the Earth functioning? Are we at the maximum of the oceanic mixing or not? That I find intriguing, and it's one of the key problems which I find very, very interesting.
Listeners can find out more, including links to the science we talked about, in my weekly show blog at ecoshock.org. Christoph Heinze, thank you for sharing your work with us.
Yeah, you're welcome. Thank you very much.
I'm Alex Smith for Radio Ecoshock.